Okay, well, welcome back, everybody, and happy Earth Day. All right. Any questions before we begin here? What I want to do is share with you the calendar I created a while back, so I give you an idea where we're at. We're way ahead, which is good. Okay, which is good. And let me share that calendar. All right. Today is the 22nd. Now you guys are in blue, the far right. Friday's blue, my yellow is my GCC class. Today is the 22nd right here. We have finished and completed chapter 14. My plan was to go ahead and jump ahead and do chapter 15 today. It's another short one. Then leave the rest of the afternoon for open for questions or anything you may want to discuss. Then next Friday, we do chapter 16. We'll get done again the first hour and a half of the time, but the time will be done again early and leave the remaining time for open discussion, review, anything you like. And then on the following Friday, which is May 6th, well, basically, if we need to continue with chapter 16, occasionally, probably not, but if we do, we'll finish it up there. And that whole day basically just opened up for your review, for your assistance. Anything that you need, we can go over the worksheets if you like, come in with questions, get you ready for either questions concerning the final exam number 5, which is for chapters 13 to 15. Chapter 16 is not in that final exam number 5, nor is it in the final exam, but there is homework for it, okay? So just, again, there is homework for 16, but the questions will not be either in exam number 5 or the final exam. All right, final exam will consist of 60 questions, all multiple choice and comprehensive, okay? So I will be here, I'm gonna be here on the 13th for about an hour or as needed if you have any questions. Remember, the final exam is not on Saturday like all the exams have been. It will be due on that Friday, the 13th. Everything is, that's literally the last day of the semester. Technically, the last day of the semester is the 12th, but I think I mentioned this before, they tend to forget about the Friday classes. But nevertheless, the 13th is our last day of class. I will be here. I'll be here for about an hour, 2 hours, or as needed if you have any questions. If not, for sure, I'll be here for an hour. If I don't hear anybody within, after the hour, I will shut it down. I will get everything graded and submitted for that Monday, which is the 16th. I will send you an email telling you, okay, I got everything graded. Numbers from my end look okay. Verify from your end, make sure everything looks okay. And then if I don't hear anything, I would submit the official final grades on the 16th, okay? Now, everything must be turned in on the 13th. If you have a challenge, I'm telling you right now, if there's a problem with the time on the 13th for the final exam, let me know early, okay? I can move it before, the 11th or 12th, but I can't move it after the 13th, okay? So plan your schedule accordingly.
Oh yeah, that reminded me, Dr. Fred. Could you
Yes.
move mine to the 12th because I'm out of town or actually, can you move it earlier because I think I fly out the 12th actually.
But I'll tell you what, I was going to say, if you need it, anybody, all of you, if you need it moved forward, shoot me an email through Canvas, tell me the day that you can do it, and I will adjust yours accordingly, okay?
Thank you, that reminded me, thank you.
Yeah, no problem. That way there's no questions because like I said, I can't extend it over after the 13th. Also, I was going through the grades today, looking at the assignments. There are some of you who have not done some of the assignments. Just a reminder that all assignments except the exams are open until the 13th. They will be late, and there was a penalty on that, but it's still, they're open. So if you're not done the assignments, you're more than welcome to go back and knock them out and get you some points. All right. Let's see. For the homeworks, for example, Canvas has a little bit of a problem when it deals with second attempts. For example, let's say you did one of the homeworks, chapter 2, 3, 4, one of the very early homeworks, and you did the first attempt and you're happy with that grade, and you just accepted, did not do your second attempt. Well, maybe now you, for whatever reason, you want to do the second attempt. You're more than happy, more than welcome to do that. What happens is if you go do the second attempt for any of the previous homeworks, Canvas treats it as a late assignment. And if you score much higher, it will put a penalty on it. And then, you'll get the lower grade. I mean, you won't get the lower grade. It won't give you the higher grade because there's a penalty for that assignment. Therefore, if you go back to do your second attempt for any of the previous exams and you do a better score on that, and you turned it on time the first time, then I will go back and remove the penalty for the second attempt to give you the higher score. Okay? Let's make sure we understand. If you did that previous assignment on time, within the time limits, and you only did one attempt, and you want to do the second attempt, and you do better the second attempt, they will be penalized because it's late according to Canvas. But I will remove the late penalty for the second attempt to give you the higher score if you turned it in on time the first time. Okay? Fair enough. Also, don't forget the nomenclature. Some of you have, maybe about half of you have done it and reached the 80%. Again, that's unlimited attempts. So you do as many as you want until you got to get the 80%. If you don't make the 80%, it sets back to 0. Is it going to affect your grade? Well, it may. Depends where you're at. If you're on the border, it most definitely will. If you're on the border, it can kick you down that 10%, or it can boost you up. Okay, so according, take that in consideration accordingly. Some individuals are in the middle, and students have not done it, and it has not affected them. That's your choice. Let me see what else. Is there anybody else? Any other questions?
Yes, I have a question, Dr. Fred. So
Yeah.
I will be at the graduation ceremony on Friday.
Okay.
So I'll probably take the final Friday morning. But if I have any questions leading up to Friday, should I join the Thursday class? Like, will you be present there in that Thursday one?
Perfect. On the 12th, they're doing a study day for my GCC. You're more than welcome. Anybody's welcome. You guys can come to any of my yellow here on the screen to ask questions. Yes, of course. If you got any questions, come to the class, present them, or email me, and I can get them answered for you.
And is this the same link? So the link we use for this class, is that the same for Thursday? Okay, thank you.
Yes, exactly the same link. No different code or anything like that. Same link.
And can you just tell me the time? I just want to write it down so I have.
From I had a senior moment there. 3 o'clock to 4:15.
4:15. Okay, thank you.
3 o'clock to 4:15. If you guys are interested to attend any of my other classes. Okay, same link. Okay. GCC link. Let me type that out so you guys can copy it. 3 to 4:15 p.m. Thursday and Friday. All right, any other questions? So yeah, we're down to the wire actually, you know, we got what, next week and 2 more weeks. And then the final week, you know, actually 3 weeks if you include the finals. All right. Any questions? Any other questions? Good questions. Yeah. All right. Well, then let me jump into chapter 15 then. Chapter 15. We're going to talk about coffee. No, we're going to talk about solutions. Okay. Solutions. Well, what is a solution? The definition of a solution. A solution is let me restate that, is a solute dissolved in some type of salt. Now, obviously, we do a lot with aqueous systems. So, you know, the classic example would be, take sodium chloride table salt, dissolve it into some container of water. Well, the solute there would be the sodium chloride, the table salt, and the solvent would be obviously the water. Okay, now, it doesn't have to be an aqueous system. It could be a non-polar system. And so it would be an oil-based material, but the same definition is solute dissolved in the solvent. The solute happens to be in a much smaller amount relative to the solvent, which would be in a larger quantity, larger amount. Most commonly, as I stated, is water system, but you're not limited to that. Okay. The one thing to remember about this, you know, we talked about polarity, something that's polar. The thing to remember is that polar dissolves in non-polar. Okay. Or another way to look at it is like dissolves like. So a compound that has polar properties will dissolve more readily in a polar solid. Okay. And something that has a compound that has non-polar properties will dissolve more readily in a non-polar solvent. We know that polar and non-polar solvents do not mix, oil and water. We know that they don't mix because we've got totally different polarity. Okay. All right. So concentration, this is self-explanatory here. This is nothing, you know, nothing complicated. Basically, you make a concentrated solution. What do? You dissolve more solute into your solvent. All right, so a dilute solution will have very little solute, and a concentrated solution will have a lot more solute. So, there's looking at the containers here, this could be Kool-Aid. You know, you got the different strength, it's just the amount of material you added into the solution. So you got a colored solution. This is a pretty good property, is colored solution, because if we know the concentration, you know, because we make the concentration of each of these containers, we can actually run in through an instrument that will measure the strength of the color, and we make a graph, a linear graph, so we can use and determine the concentration of unknowns. So, but that's a side note. Okay. Examples. Now we're not limited because we tend to think, okay, solute, like the example I gave was with a solid and a liquid, a sodium chloride and water. But we're not really limited to that. There's different types of solutions. For example, a gas in a liquid. Classic example would be a carbonated drink. Okay. we got gas that's been dissolved and placed into a liquid, giving you carbonated drink. Or we can have liquid and liquid combination, where you got an alcoholic drink where you got alcohol and water. Okay. The one I spoke about is actually having a solid in a liquid, and here you can make salt water. But again, you're not limited to ionic compounds, okay? You could be covalent compounds and give you a solid dissolved in a liquid. Or you can have a combination of gas and a gas. Our air is made up of a variety of different gases of different concentrations. So nitrogen, oxygen are the most abundant in the air. All right, and then solid and solid. People don't tend to think that it is a solution, but by definition it is. Because, for example, iron, or steel, I should say, is a combination of a mixture of iron and some carbon. And carbon is introduced into iron because iron in itself, pure iron itself, has no strength. Very weak material. We couldn't put a building together using pure iron. And so they make what's called an alloy. An alloy is a solution of a metal, a solid and a solid. Steel is an alloy. Brass is another example of an alloy. Brass is an alloy of copper and zinc. Okay. So, all right. So, as I stated, bringing in what we learned about polarity, we can make the following comment here, that polar solutes dissolve in polar solvents, okay? And the converse is true, that nonpolar solutes dissolve in nonpolar solvents. For example, we know that nonpolar and polar do not mix. Here's a picture of a classic example of an oil spill. Oils are made up of mostly hydrocarbons. Remember, hydrocarbons, these are compounds that are made up of nothing but carbon and hydrogen, which are nonpolar bonds. And having nonpolar bonds, hydrocarbons or oils tend to be very nonpolar, very nonpolar. Okay. Now, when we talk about something that's, when we take two liquids and we kind of mix them, we put them together and they mix, we use the term miscible. So miscible is a term used to describe when two liquids mix together because of their relative polarity. When two liquids do not mix together, like oil and water, that is, we call that immiscible. Not to be mistaken with respect to soluble, where when we use the term soluble, we're talking about a solid and a liquid, okay? More on that here in a second. So if a solid is dissolves in a solvent, then that is described as being soluble, okay? If it's not, then obviously it's insoluble. And we use the solubility rules with respect to ionic compounds and water solvents to determine whether something is soluble or insoluble. All right, so, well, what we have here is a table. On the first column, we have a solvent, okay? And across the column on top, we have four different solutes, okay? So the question here is, can we dissolve it or not, okay? So we're going to see if we take some HCl, okay, hydrochloric acid, and remember this guy, NH3, good old-fashioned ammonia, okay? But to determine whether it will be dissolved or not, what we need to determine first is it polar or nonpolar? Okay. And so HCl, we know is polar. We have two atoms, dissimilar atoms, okay? They're both non-metals, which means we got a covalent bond. And being dissimilar, we automatically can state that the HCl is polar. Eventually, when you start, you're using a lot of chemistry and you become more familiar just by sight, HCl, it's polar, okay? Because we got two dissimilar atoms here. Ammonia, we went in a while back, we way back when we were doing the Lewis dot structures, we determined the Lewis dot structure for ammonia. And then to refresh your memory, we came up with this following Lewis dot structure, and they had lone pair in the center atom. Those two dots, for refresh your memory, represent lone pair. At that time, I stated anytime you do a Lewis dot structure and you end up with a lone pair on the central atom, 99% of the time you can say, I got a polar compound. All right. And so I got ammonia that's polar. I got HCl, which is polar. Then I would anticipate those two to mix. Okay. All right. Well, let's figure out the polarity of the rest of the solid. The next one is C12H26. Okay. You may not know what that is. That's okay. But hopefully what you do recognize now is I have a compound that consists of nothing but carbon and hydrogen bonds. That's it. And having nothing but carbon and hydrogen bonds, okay, this one here represents 12 carbon chain. There's 12 carbons in the chain, and then the hydrogen's bonded all around the species. Very, very non-polar. Why? Because the carbon hydrogens are non-polar. The carbon hydrogen bond is non-polar. So therefore, we have a non-polar solvent, okay? Non-polar solvent. Br2 is a diatomic species, two bromines bonded together sharing that bond, okay? All diatomics share that bond equally, and therefore all diatomics are non-polar in nature, okay? So ammonia is polar. The hydrocarbon is nonpolar and bromine is nonpolar. One of the solutes here is polar, HCl. The next one, which is I2, which is iodine, again, diatomic, that is a nonpolar solute, okay? Trichlorophosphorus, phosphorus trichloride, okay? Well, to determine whether that is polar or nonpolar, if you don't know it by sight, you literally have to do the Lewis dot structure. And when you do that, you end up with this structure. Remember, these lines represent lone pair, and then we got a lone pair in the central atom. Okay, again, we got phosphorus chlorides, we got polar bonds, and we got a lone pair on the central atom. Automatically, we got a polar solute here for PCl3. And finally, the last one is methane, which is one carbon, 4 hydrogens. The fact that you see nothing but carbon and hydrogen should tell you I got a nonpolar solute. So I got 2 polar solutes and 2 nonpolar solutes. And then I got 1 polar solvent and 2 nonpolar solvents. Now, once I define and once I recognize what is the polarity of all the entities involved here, then I go back to like dissolves like, and keep it in mind that polar dissolves nonpolar. Let me restate that. Nonpolar will dissolve in nonpolar solvent, and nonpolar solutes will dissolve in nonpolar solvents, okay? Like dissolves like. So the first one, there's the polarity we just talked about. The first one would be yes. If I were to take a little bit of HCl and dissolve it into ammonia, yes, it should go into solution because of their mutual polarity, okay? With iodine, it wouldn't, because iodine is a nonpolar species, whereas ammonia is polar. PCl3 being polar, we would anticipate that yes, it will dissolve in ammonia, in solution, any solvent of ammonia. And obviously methane wouldn't dissolve very well because CH4 is nonpolar, okay? C12H26 as the solvent would not accept HCl very well with respect to solubility because of difference in polarity. But iodine, no problem because they're both nonpolar. Not very well with PCl3 because of differences in polarity, and no problem with CH4, again, because of polarity. All right. Bromine, acting as a nonpolar solvent, would not dissolve HCl very well, but no problem with iodine, problem with PHCl3, and no problem with CH4. Okay, like dissolves like. Now, back in the day when I was younger, and my sisters were using this makeup thing, if you forget about this polarity, the one thing is, and it could be true to today, I'm not sure, you ladies can maybe enlighten me, but some of the makeup was pretty non-polar. In other words, it is more like hurricane-proof makeup that once you put it on there, all the rain and stuff would not make it run. It would not dissolve. And so you basically needed some oil, if you will, oil-based material to remove it. And then some makeups were, a little bit cheaper material, I believe, a lot more polar. And so any bit of tears or rain would cause it to run. It has a lot more polar character. So, okay. So that, if you tend to forget about like dissolves like, maybe that could remind you about what dissolves, what doesn't dissolve, okay? All the makeup, because I recall my sisters used to have all that Noxema at night, looked like it was Halloween every night. Because they had a lot of the stuff on them to get the makeup off. All right, so using the terms miscible, immiscible, soluble, insoluble. Remember, using the term miscible and immiscible deals with liquid and liquid. Using the term soluble and insoluble deals with the term using a solid and a liquid, okay? And so here we got a polar liquid and a polar solvent, okay? So it would be miscible because they're both are liquids, okay? With respect to a polar liquid and a nonpolar solvent, which would be immiscible. So a classic example would be oil and water. If the oil was the solvent, large in quantity, you add some water to it, it's not going to mix. It's immiscible, okay? Nonpolar liquid, immiscible with a polar solvent, but miscible with a nonpolar solvent. Now, with respect to a polar solid, okay, polar solid, it would be soluble in a polar solvent. Okay, a polar solvent would be a covalent compound that is obviously solid, but polar because of the nature of the bond formation there. It would be considered insoluble in a nonpolar solvent, okay? Nonpolar solvent would be insoluble in a polar solvent, but it would be classified as soluble in a nonpolar solvent. With respect to ionic compounds, now remember, ionic compounds are metals and non-metal combinations, sodium chloride, okay? Any metal with non-metal. And so if you have a polar solvent and a ionic compound, it depends, okay? We would check the solubility if the polar solvent, check with the solubility rules, if the polar solvent was an aqueous system, okay? And it will be classified as insoluble if it's a nonpolar solvent. A good example of that is you try to take, you're cooking some eggs and you throw some oil in your pan, throw some table salt. You'll see the table salt will not dissolve, okay? Because you have an ionic solid and a nonpolar solvent. All right, any questions on this? It's basically kind of kind of direct you as to the use of the term miscible, immiscible versus solid and soluble and insoluble. Now, with respect to the dissolving process, and here we're talking about aqueous systems. We did have a picture of this before, where you have sodium ions, in this case sodium ions, but it could be any metal ion in soluble water, totally solvated or totally dissolving the ion. And again, based on the polarity in the dipole of water, where you got a partial negative, okay, the partial negative of the water interacting with the full-fledged charge of sodium. So here we call those IMF. This was the ion dipole force. Okay, the ion here, in this case sodium, and then we briefly talked about the chloride on the other end with the full negative charge interacting with the positive, partial positive side of the water molecule. Okay, now, with respect to concentration, we're talking about a solute in a solvent. Now, we have two different types of units for concentration. One is called the mass percent, okay? Mass percent. And the other one is called molarity. All right, now way back when we were talking about pH, okay, we introduced this concentration unit, molarity. When we were talking about pH, remember it was we had the proton and we had a bracket on it, okay, and we introduced that, where we had the concentration, the molarity of the proton, which has the units of moles per liter. The fact that you are using moles, okay, since you're using moles, then that might suggest you need the molar mass. Okay, so here we go. We're probably going to use grams, be given grams, okay, and we need to convert that to moles. All right. And if we need to convert that to moles, then more than likely we're going to need the molar mass, all right, for that compound. And if we need the molar mass, that means that we need to add up all of the atomic weights for all the atoms in that compound, sum them up, okay, and that total atomic weights would give us the molar mass. The other I put green, this is grams. The other aspect is this. If we go from grams to moles, we actually divide it by the molar mass, okay? Remember that when we were doing these conversions on the calculations? Grams to moles, we divide by the molar mass. And moles to grams, we multiply by the molar mass. Because remember, the molar mass was, unit-wise, molar mass was grams per mole. Okay. So carbon had a atomic weight of 12.01 grams per mole. Okay. I remember what 1 mole was, 6.02 times 10 to the 23rd units. All right, here you thought you got rid of the moles, and here they come back. All right, so how do we do the mass percent? By definition, the mass percent, there's a lot of drinks out there that if you look at the label, you'll see that, well, alcohol is a good example. Wine, you'll see the percentage. A lot of them are mass percent, some of them are volume percent. Instead of the mass, they're using volume, okay, to give you the percent, maybe amount of alcohol in the wine or so forth. By definition, the mass of the solute is divided by the mass of the solution. Now, the solution, I repeat, is not the solvent by itself. Remember, the solution is the combination of the solute and the solvent, its total weight. And so, for example, if we take 15 grams of, let's say, potassium nitrate, I'm really concerned about the formula here, but this is mass percent. We don't need the molar mass. All we need to know is the weights of the solvent and the weights of the solute, okay? If we take 15 grams of potassium nitrate and we dissolve it in 135 grams of water, the way we calculate that is we take the 15 plus 135, which goes in the denominator, and then we got the 15, which goes in the numerator, and then we multiply by 100, and that would give you the mass percent, where in this case, if we take 15 grams of potassium nitrate and we dissolve it in 135 grams of water, we have a 10% solution by weight. And that's why you clarify it by weight, okay? Some of you who may be working in the health industry as nurses' aides, you probably know that you have out there a saline solution, okay? And that is made up of 0.9% sodium chloride, okay? That is the optimum concentration of a solution of sodium chloride that you can inject into your veins without causing damage to your cells inside. Okay, it has to do with the amount of ions in solution, the amount of ions in your cells. So either if you put in the wrong solution, you're going to shrink up your cells or you're going to blow them up. So 0.9% is the optimum concentration of sodium chloride. All right, so sometimes, well, let's do an example here. But let me repeat. Let me back up for a second. Okay, a lot of times you're given the solute amount and you're given the amount of water that you're going to use to, and they need to calculate the mass percent of the solution. Occasionally, you may have a scenario where you know you need to make a 10% solution, and you know you got 15 grams of potassium nitrate to work with, but you don't know how much water to use, okay? And in this case, obviously, it's 135 grams, but it's given to you. It's occasionally you may not know how much water you need, but you do know that you need to make a 10%, and you know how much sodium, or in this case, whatever solute you have, you know, the 15 grams, and you need to know how much water I need to use given the amount of solute to give me that percentage. So when that occurs, we need to do a little bit of algebra, okay? Not anything complicated. Here is what I was talking about. They're asking you, clear this up here. They're saying, how many grams of water do I need if I need to make a 5.00% saline solution, and if I have 10 grams of water, excuse me, 10 grams of the salt, okay? And let's assume this is sodium chloride, but it could be any salt, okay? So how many grams of water are needed? So what we do is we set up our problem as follows, because we know, based on definition, that the percentage is the weight of the solute, which is 10 and 10. We're given that right there, okay? This is the 5% that we're trying to make. We're going to multiply this whole unit by 100. And what we don't know is the amount of water, and that is what we need to calculate, okay? So you got a little bit of an algebraic equation. Now, when it comes to algebra, I haven't taught algebra before with physical therapy students. I always tell them, there isn't a wrong way or a right way. Let me restate that. There's multiple ways to solve for a variable. okay? And so sometimes it's, one way is not the best way to go, and sometimes it is, okay? So what we have here is a algebraic equation that we need to solve for x. So the way your textbook does it is, what they did was they took the whole quantity in the denominator, 10 plus x. I'm just going to 10 plus x, and multiply both sides by that quantity, okay? What that means is that 10 plus x and the 10 plus x in the denominator cancel out. And so now you have the 10 times 100, which is given there. And then on the left side of the equation, remember in algebra, whatever you do to the right side of the equation, you got to do it to the left. And that's why they ended up right here with 5.00 times the quantity 10 plus x, okay? They're trying to simplify this and make it as easy as possible. And this is one way to do that. Okay, the next step that they do is they simply multiplied out the 10 times 100. Okay, and so that's 1,000. That's how they got 1,000. All right, now from this point you can attack this problem any multiple ways. One way is you take the 5 and you multiply here times 10, then multiply the 5 by 5x, and then solve for x in that manner. That's one way to do it. Another way to do it is what your textbook did. What they did is they took this side, the left side, divided by 5 on both sides of the equation. And I got rid of the 5 there and the 5 there, okay? That's one way to do it. And the other way to do it was to take 50, multiply, like I just said up there, plus 5x. That gives you 50 is equal to 1,000. Okay, and then I can go 5x equal to 1,000 minus 50. Then I can take x and take all that 1,000 minus 50 and divide by 5, and I get to the answer. This is one way to do it. The other way is to do what they're doing, going from here to here. Okay. And then once they did that, you can see the 5's cancel out, and then they end up with the equation as 10 plus x equals 200, because that is 1,000 divided by 5 to give you 200. Okay. Now you have the quantity x isolated, but you got 10 on the left side, so you subtract 10 on both sides, minus 10. Okay, these 10 cancel, and then you end up with x is equal to 190, right? Okay. But let me clear this up. They wrote it in scientific notation because of sig figs. And so it's 1.09 times 10 to the second grams, or 190, because your answer should have 3 sig figs. Okay. Now, how do we know that number is correct? Well, no problem. As any algebraic equation, you would take the x that you solve for and you plug it back into the original equation, okay, and then do the math on both sides. And what should happen is you should end up with 5.00 is equal to 5.00, which is a true statement. Okay, if you throw x in there, you're 190, and you don't come up with that, then more likely you made a mistake someplace, and along the steps you may need to go back and check it out. So the x, the 190 is correct. And so what this says is this, that I need to take, when I take 190 grams of water and I take 10 grams of the salt, I end up with a 5.0% solution by weight. Okay, by weight. Any questions? Okay. Okay, so that is the concentration, percent concentration by weight. Molarity is, as I mentioned earlier, we need to determine, it's defined as the moles of solute divided by the volume of solution, typically in liters, okay? Typically in liters with respect to the solution. And so those are the units, are moles over liter. So given any problem, we need to determine first the molar mass, okay? Because in this case, they're telling you calculate the molarity of 9.99.
Could you go back a slide for a second? I missed one.
Sure. Right there. How's that?
Perfect. Good. I just missed the mole over the liters. Thank you.
Okay. Yeah, I don't, that should be written with moles. I don't know why MOE. That is shorthand for some books use that as shorthand for mole. And I'm like, well, just throw the E in there too. You got one more letter. Anyway, moles per liter. All right, so in this example here, they're telling you calculate the molarity, and this is how you do it for any compound, any solution. They're using the example of potassium bromide. Well, first of all, to figure out the molar mass for potassium bromide, you need the formula first, right? So if you don't know the formula, you don't know the molar mass. So we got to go back and figure out what is the formula. So we got potassium and we got bromide, definitely an ionic compound. I always recommend to put everything in ionic form first so that you make sure you put them together in the right ratio. We know that potassium is in group 1, okay? It is a group 1 metal, therefore it has one valence electron. So when it becomes ionic, it will lose that one electron and become isoelectronic with argon, which has 18 electrons. So when that happens, it's going to end up with a positive charge, okay? The bromide, nonmetal, or bromine is a nonmetal. It is in group 7. Being a nonmetal, it will gain an electron, okay? And therefore will have a -1 charge, because by gaining 1 electron, it now becomes isoelectronic with krypton. It's the metal in front of it. Not the metal, the noble gas in front of it. And so now we know that each one's a plus 1 and -1. I can simply just put them together in a 1-to-1 ratio, okay? Once I got the correct formula, now it's a matter of figuring out the molar mass, which is potassium is 39.1 and bromide is 79.9, okay, grams per mole. So we got 0, 10, okay, 18, 19, 10, 11, 119.00 grams per mole. My math is right. And that is the molar mass, okay? And we're going to take 9, write down what we're given, 9.9 grams of potassium bromide, okay? We need to determine how many moles of potassium bromide that consists of. And so therefore I know I need grams in the denominator, moles in the numerator. Okay, so it's 119.00 grams divided by 1 mole, so 1 over 119.00. My units of grams cancel, leaving me with moles of potassium bromide. So my units are okay. Now it's a matter of plugging it into the overall the overall equation, which is moles per liter, okay? And we're given the liters here as 2.50 liters. So that's given the moles of potassium go on the top. You do the math, keep track of your sig figs, and we're good to go, okay? Now, in this case, they gave you the volume in liters, but you know, you can't have an example where they give it to you in the volume that is in milliliters. Well, what you do is, don't forget, you need to convert that milliliters to liters. And so remember the conversion factor. 1 liter is equal to 1,000 milliliters. Okay, just like in 1 meter, there are 1,000 millimeters. Okay, in 1 liter, there's 1,000 milliliters. Okay, so let's see the textbook. All right, so yeah, we got the correct molar mass. You can see 9.99 grams per grams of potassium bromide divided by 119. I wouldn't truncate anything. I wouldn't do any truncate as far as sig figs. Use all the digits. Keep it in mind that the final calculation, you know, would have, you got 3 sig figs here and 3 sig figs here. Okay, and so your final answer should have 3 sig figs. All right, so don't truncate, calculate your moles, and then you tend to truncate it here. Don't do that. Take all the digits and then truncate at the end after you do the division. All right, so if you went out to the lab and you weighed out 9.99 grams of potassium bromide, okay, and then you had a special container, which is a volumetric flask that had a mark, the very specific mark at 2.5 liters, you would put the potassium bromide into the container, and then you would dissolve the container with water, add water, and get it all dissolved, and bring it up to that mark on that container, and then at that point, you would have a 0.0336 molar solution, moles per liter, or molarity solution of potassium bromide. Okay. All right, so just a quick reminder to do the worksheets. That'll really get you more practice. Okay, and we'll do one more here. And we'll basically probably do one more, and now guess what? That'll be the end of chapter 15. All right, so what we have here is calculate the molarity. If you take 5 grams of sodium phosphate and you dissolve it in 255 milliliters of solution, okay? And so what I do when I cut these calculations to remind me, you know, especially when I first started doing these type of calculations, chemistry, is the definition of molarity, which is moles per liter, okay? So I got that in the back of my head. Those are the units I got to strive for. All right, I can see here that I have 255 milliliters, so I'm going to have to convert that to liters. And so I need a conversion factor that 1 liter is equal to 1,000 milliliters. Okay, so I got to write that down because I know I'm going to need that. Okay, I got 5 grams of sodium phosphate. Well, I first need to determine the formula for sodium phosphate. Now, notice this is not phosphide, IDE, it is the ATE, the 8. So that should direct you to the table on the periodic table for the polyatomic ions. And you'll find that in there, and that will be PO4 -3. Okay, that is the phosphate ion, polyatomic ion. The sodium, as the case with potassium, is in group 1. And the sodium would have, once it becomes ionic, would have a +1 charge. Okay. And so now I can put the two ions together, the cation and the anion, the correct ratio. Since sodium has a +1, I need 3 of them. I need 3 positive sodiums to cancel out the 3 negative overall charge of the phosphate. So this 3 becomes the subscript for sodiums, and the formula is Na3PO4, okay? Now I have the formula. With the formula, now I can calculate the molar mass by looking up the atomic weights for all the atoms. So I got 3 sodiums. Okay, each sodium's at 22.99. I got 1 phosphorus and 4 oxygens. I can tally all that up. That gives me the molar mass for sodium phosphate. Okay, so I can do the following. So if I do that, I end up with a molar mass of 163.94 grams per mole. All right, so I start with grams. Just see what I'm doing. I'm dividing by the molar mass. And that gives me 0.030499896 moles. So just, carry it through as many digits as you want. Don't truncate anything until you are done at the end. Now, keep it in mind, you got 2 sig figs here, 3 sig figs there. So your answer should end up with 2 sig figs, okay? Remember, we don't use the atomic weight or the molar mass to determine significant figures, okay? And we don't use the conversion factors of 1 liter is equal to 1,000 milliliters because those are exact numbers. So the 5.0 grams and the 255 are both measurements and therefore would play a role in determining the final sig fig digits. Right, so the next is to convert the volume of 255 milliliters to liters. And we take the conversion factor in 1 liter is equal to 1,000 milliliters. Notice my units. All this time, don't forget that technique, keeping track of your units. Notice my grams cancel here in the first one. The second one, my milliliters cancel. So I got units of moles up top up here, and then I'm going to have units of liters, okay, which is what I'm striving to get. Okay, so now I can do the math, and I end up with 0.12 moles per liter, or you can just, write that as 0.12, then with a capital M. That is the symbol for molarity. All right. So again, if I go to the lab and I weigh out 5.0 grams of sodium phosphate, and then I dissolve it with 255 milliliters of solution, which more likely here in this case would be water, because we're dealing with ionic compounds. And that gives me a concentration of 0.12 moles, molarity. Okay. All right. Any questions about how to calculate molarity or the percent composition? Questions about miscible, immiscible? No? Don't forget your assignments. There is a practice final exam on the website. I think I also put it in the module, final exam module on campus. Okay, so you might use that. So that being the case, we are done with chapter 15. Congratulations. Short. All right, well, I tell you what. I won't, as I promised, I won't jump into 16 until next Friday. If you have any questions, this is a good time. What I'll do is when we take a little short 50-minute break, you can look and see if you have any questions. If you don't, have a good weekend. I'll see you next Friday. All right. Other than that, let's say it's 1 o'clock. I'll be back here at 1:15. If you have questions, we can go over them. If not, We can talk about Earth Day. I don't know, whatever you want to talk about, chemistry.
Have a great weekend. Thank you, Dr. Fred.
All right, thank you, guys. All right, I'll be back 15 minutes.